Okay, so second to last unit for us. I really love the first unit in this class when we talk about sets. Just, I don't know, that's just something I enjoy. But this is probably for all of you, as far as your lives and whatever you do for your career and being able to read the news and stuff like that. This unit right here, this chapter 11 that we're going to go through in the book, this is probably one of the most useful things that you will learn in this class. This probably, and being able to work with units when we did the dimensional analysis. Being able to understand probability even just a little bit helps you understand data. It helps you understand a lot of stuff that we are presented and giving you the ability to critically analyze it. It's super important, like, because so many messages are coming at us every day. How do I know if somebody's using statistics and probability correctly or incorrectly? Well, you're going to get a little bit of a snippet of that. And my hope is if you have to take another math class and you don't want to take the MGF 1107 with me in the fall, take a stats class. It's worth your time to be able to understand how people are trying to communicate to us. So here we go. First thing is an experiment. An experiment is a controlled operation that yields a set of results. So where we're going to start talking about probability is with this idea of an experiment. And so the set of all possible results of an experiment is called its outcomes. And lastly, an event. These are just a few words you're going to need. An event is a subset of the outcomes of an experiment. So in this first section, we're just going to do one thing. We could do more today, but every other section, I think there's 8 sections in this unit. Every other section requires you to be able to do what we do in this first one well. Okay, that's why I'm just doing this one section so that you can have some time to go and do your homework and get up to date on this. So we're going to look at experiments, either experiments that have already been done or experiments that we're just going to think about what would happen if we did do them. And then each experiment that is done has a set of possible things that could happen called its outcomes. And then we will concern ourselves with some segment of that. So for instance, okay, just because I don't want this to seem too overwhelming, because it really shouldn't be, we're going to look at the experiment of rolling a die. Now, die is singular for dice. Okay, so it's just one die. So we're just going to have one six-sided die. So the experiment is rolling a die. And so then what are the outcomes? The outcomes are the set of possible things that can happen. So when you play Yahtzee or Monopoly or any other game that you like to play, what are the outcomes when you roll a die? Yeah, 1 through 6, right? So I'm just going to write that down. 1, 2, 3, 4, 5, 6. Then we could talk about events that are some subset of this. So some events, just examples of them, because this is the lingo and how things are going to look as we go through this, unit. Events could be rolling 02. Okay, that is a subset, just that one event. Or I could talk about rolling an even number. Or just one more example, rolling a number greater than 2. So that is just a very simple example of an event. We're going to start simple with our probability. But like I said before, probability is used all throughout our lives, probably just not even aware of it sometimes. So hopefully you get a little bit of an understanding. Okay, so for instance, empirical probability. So we're going to start with this. Empirical probability is determined through the actual results of an experiment. It's the probability of an event the next time the experiment is performed. So for instance, This just occurs to me because when I was younger and more fit, I used to like to play baseball. And so if you're familiar at all with baseball or any other sport, any of the statistics there. So if somebody has a 0.250 batting average, that means that the probability they get a hit the next time is going to be 0.250. That's all probability. Okay, so anything like that is a use of probability in your daily life. So the empirical probability is you look at the actual results, things that have actually happened. So to find and calculate the empirical probability, here's what you do. The probability of our event. Okay, so we're going to use capital P as our designation for probability. In the parentheses, we will summarize whatever event we are calculating the probability of. And so all you're going to do is you're going to say, okay, the number of times E occurred, and then you're going to divide it by the total number of times the experiment was performed. So our empirical probability, empirical means that I'm actually looking at the experiment, I'm actually looking at data, and then the probability we calculate is the probability of what's going to happen the next time the experiment's performed. So here is a real simple example, example 1 right here for me. I'm going to pretend that I've tossed a coin 100 times. In math, the word fair, that is not a moral statement. The word fair means an equal chance of occurring. So if I'm tossing a fair coin, that means that it's equally likely that it's going to land heads or tails. It's not weighted so that I would get some sort of skewed result. So in 100 tosses of a fair coin, 44 landed heads up. So we're going to determine the empirical probability of the coin landing heads up. I don't think this is too big of a deal I think I wouldn't even have to do this and you all could get this, but just want to show you the notation. So I'm going to calculate the probability of getting a heads on my coin. And all probability is just a ratio. Okay, this is the thing to remember, whether it's empirical, and we're going to see in a little while theoretical probability, where you don't actually do the experiment, you're just looking at what should happen. It's the same thing. How many times does this event right here, heads, happen according to my problem? Perfect, 44. Out of how many total times did I flip the coin? 100. The results of probability are always written in one of two ways. I do not care on the test which way you do it. When you go through my math lab, just be sure you give the results in the way they instruct. Okay, so one of two things you're going to do. You're either going to reduce the fraction. So if you're going to give me a fraction, reduce this fraction. So I can divide 4 into the top and the bottom. 4 goes into 44 11 times. 4 goes into 125 times. Okay, so if you're going to give a fraction, make sure that you reduce it. This gives you the reduced ratio. You're going to get 11 heads up every 25 times that you flip the coin. So that's what my fraction's saying. Or you can give a decimal, and in this case, the decimal is just going to be 0.44. All right. We're just going to do a bunch of examples because I don't think probability is necessarily hard, but I think that you have to practice it. And I want to make sure we get enough practice because this forms the whole rest of this unit, all the 7 other sections. So exercise 1. Just going to read through it real quick with you, and then I'm going to let you do the 3 parts to it. It says, at the Virgin Music Store in Times Square, 60 people entering the store were selected at random and were asked to choose their favorite type of music. Of the 60, 12 chose rock, 16 chose hip hop, 8 country, 24 some other category. Determine the empirical probability that the next person in the store favors each of those types of music. And then either write your answer as a reduced fraction or make a decimal out of it. All right, so I'm just going to ask you these simple questions. If you do not understand where the answers to these questions are coming from, that is a great thing for you to ask. So the first thing we're going to do is, what's the probability the next person through the door likes rock music? So of my empirical data, okay, I've got data for this. How many people like rock music? 12. Okay, these 12 right here. Out of how many? Perfect. And I can reduce that. I think 12 actually goes into both of those. 12 goes into 12 once. 12 goes into 65 times. But if you did not, you don't have to do both of these things. I'm just doing both because I don't know what you chose. What I would do if I were you is I just pop it into the calculator. That would be my suggestion. And then 12 divided by 60, just confirming, is going to be a probability of 0.2. One person out of every 5 people that goes into that store is going to enjoy rock music according to this data that I have. How about hip hop? How many people going into the store, out of the store? I don't know which way they were going. How many like this? 16, fantastic. Out of the total of 60, 4 goes into both of those. 4 goes into 16 4 times. 4 goes into 60 15 times. And if you made a decimal out of it, like I expect probably most of you do, here's something that I'm just going to give you a little instruction. My preference, this will be my instruction on the test, is we want to give enough decimal places that we can understand and get a full picture. So I don't want to round to too few decimal places. And I also don't need too many, because at some point it stops having meaning. So I like 4 decimal places. Okay, so I'm going to round this to 0.2667. Is the probability of that happening. Okay, the last one. What's the probability of other? So what's the probability that somebody chose something other than rock or hip hop or country? How many is that? 24, fantastic. Out of the 60. And so again, 12 goes into both of those. 12 goes into 24 2 times. 12 goes into 65, but you probably just put 24 divided by 60 into your calculator and got 0.4. Are we doing all right so far? All right, beautiful. If you're not, let me know. Let's turn the page. Here's another exercise for you. This time we're looking at the results of some sort of drug trial. So go ahead and read through and do the 3 parts to exercise 2, please. right, so going through this problem, companies testing this drug, it was given to 500 individuals. The outcomes were 379 had reduced blood pressure, 62 it was unchanged, 59 it was increased. So I'm just going to go through. If your numbers differ from mine, let me know. Let's talk about it. So the probability that the next person, if you were prescribed this drug, the probability that would help you and reduce your blood pressure would be 379 out of 500. And so then we just pop that. I would not reduce numbers like that. And in fact, I don't think this one does anyway. I think that already is reduced. So that's 0.758 would be that probability right there. Okay, the probability that it's unchanged would be 62 out of 500. Again, I wouldn't even bother reducing those when the numbers get large. I would just go right to my decimal, 0.124. And then last but not least, the probability that was increased would be 59 out of 500. And when I do that division, it is 0.118. Anything we need to talk about there with that exercise and empirical probability in general? Because that's the extent of empirical probability. We're going to turn our attention to something that's a little more commonly used. All right, well, anytime we're talking about probability, whether we know it or not, we are using what's called the law of large numbers. Okay, so this is something in statistics and probability that is just assumed for everything. What the law of large numbers says is that probability statements apply to a large number of trials. Additionally, as the number of trials increases, the empirical probability, which is our experiment, approaches what's called the theoretical probability. So what this means is, to refer back to my baseball example, because I enjoy baseball, if in the first at-bat of the year you get a hit and you're 1 for 1, that means you have a 1.00 probability. Well, you've only got a sample size of 1. Okay, so that doesn't mean the probability that the next time you get up you're going to get a hit is 1, like you have to get a hit. Okay, probability only has meaning for a large number of trials. That's why you have a better feeling for how your baseball average or your shooting average or whatever it is you like to do, that you've got some sort of measurement. It has more meaning the more things that you do. So just as an example, this is just a chart from the book. I'm assuming that they did this via a computer just to show you. So in this, somebody flipped the coin 10 times. And since there's 2 sides to the coin, you would expect 5 of them to be heads. But notice, we only missed that by 1. We got 4 heads instead of 5. Only missed the target by 1. But notice the probability. The probability is 4 out of 10 or 0.4. Okay, so that's a whole tenth below what we would expect. So now notice, we flipped the coin 100 times, or we had the computer flip the coin 100 times. The expected number of heads now is 50. Half of them is what we would expect. This time we missed the mark by 5 times, right? We got 5 fewer. So we've missed more than we missed the previous time. But the thing here is I've done this experiment more times. So each of those 5 means less in the whole scheme of things. So now the probability is 45 out of 100 or 0.45. So even though we missed 5 times instead of just 1, we're actually closer to what we would expect, 0.5. And you can follow this all the way down. I'm not going to bore you any more than I probably already am. But if you flip the coin 100,000 times, so you had a long weekend and you didn't have anything else to do, you would expect 50,000 heads. Notice you missed it by 230. There were 230 times that you didn't get what you would expect. But because we flipped the coin so many times, each of those is almost meaningless at this point in and of themselves. And so the empirical probability becomes 0.49770. So each time, even though you're missing how many you would expect by more and more and more, the empirical probability is getting closer and closer and closer to 1/2. And so that's just what I describe in this little paragraph below. I'm not gonna read that. You can read that if you're super interested or need to get more clarification. So the whole point there is that you need to have a large number of trials for probability to have meaning. So moving on, that takes us to the realm of what's called theoretical probability. So theoretical probability, which is just what the blanks are, because I couldn't think of better words to make the blanks in this case. The theoretical probability is calculated by considering all the equally likely outcomes. Now, it doesn't matter if you're doing empirical or theoretical. The words here that I give you for calculating this probability are going to be slightly different, but the bottom line is the ratio is going to be the same. Okay, it's going to be the number of things that agree with your event divided by the total number of things. It's successes divided by the total. That's always your probability. So the theoretical probability to calculate this, when I want to calculate the probability of my event E, I am going to first take the number of outcomes in E. So the number of outcomes in the event that I'm considering, and then I'm going to divide that by the total number of outcomes. All right, so I've got an example, and then we're just going to spend the rest of our time here just doing various examples. And again, if you have any question, I'm only doing this one section. We could do more in class today. You're probably going to get out a little early. The reason I'm doing this is I want you, please, to practice this, take your quiz, so when we come back to class on Tuesday and we get rolling through this, everything else uses probability in this chapter. So if you want to be successful, practice this. That's just what I'm asking you to do. So here's my example. This goes back to my very first example. We're going to roll a fair die, 6 sides. We're going to determine the probability of each of these things. So first, what's the probability that I roll a 2? Right. You can look back on the first page if you would need to, but we listed out all the possible outcomes. There was only 1 2 out of the 6 possible outcomes. That is complete. You don't have to do any more, but if you prefer decimals to fractions, then that is going to be 0.1667. I'm going to round to the 4th decimal place to give me a comfortable amount of accuracy. The next one I'm going to do is the probability of an even number. Well, thinking about my die with 6 sides, how many of the sides represent an even number? 3 of them out of how many total sides? Great. Okay, and so 3 divided by 6, you pop that into your calculator, that's 0.5. Is everyone catching on to what this is? A number greater than 2. Okay, so I'm just going to use symbolism. I'm going to use the greater than symbol, then 2. How many numbers are greater than 2 out of my outcomes? Okay, 4 of them out of 6, fantastic. Again, that you can reduce that to 2/3. I'm going to make that into 0.6667. So you can see there's variation in probability. So then the next thing, the purpose of these next 2 examples is to give us a feel for what's my range, what's probability telling me. Okay, so the probability of a 7. Well, in my list of outcomes that we made earlier, how many of the results were a 7? None of them. So 0 out of 7. Well, if you go into your calculator, 0 of something divided into 7 parts is 0. So when something cannot happen, okay, when something's impossible, as rolling a 7 with a 6-sided die, the probability is 0. Okay, so I'm just going to put in parentheses here. Okay, if an event is impossible, has a probability equal to 0. Well, then the next one, similarly, a number less than 7. Well, on my list of outcomes that we made earlier, how many of the outcomes were less than 7? All 6 of them, right? So 6 out of the 6. Well, what's 6 divided by 6? 1. Okay, well, that's something that has to happen. Okay, so if something has to happen, if there is 100% chance that it's going to happen, then the probability is 1. So in an event that is certain has a probability equal to 1. So what we have there is an important set of constraints for our probability. The probability of any event, okay, will always fall in this range of values. Probabilities are always going to be bigger than or equal to 0. And probabilities are always going to be less than or equal to 1. You're never going to get a negative probability. You're never going to get a probability of 5 or 19. Okay, it's 0 to 1 always and every time. And so we can see from our example, the closer a probability gets to 1, so this 0.667, the closer a probability gets to 1 means what would you say? The more likely it is to happen, right? So that's why when you're watching sports, you want somebody to shoot free throws that has a empirical probability that's like 0.95 rather than the person with 0.47, because their probability they're going to hit their next one is higher. Okay, so it's all probabilities, especially in sports. That's why there tends to be a lot of sports examples in this chapter. All right, so here's your next one, exercise 3. You're at a picnic and there's a cooler with 100 ice cream cups of various flavors. Go ahead and find the probability, the theoretical probability of each of those, please. All right, so there's 100 cups. I kept the numbers on this first example nice and relaxed. So there's 40 vanilla, there's 20 mint, there's 30 strawberry, there's 10 chocolate. So in theory, if we did this a large number of times, what's the probability that I would randomly pick a strawberry cup? Yep, that sounds great to me. There's 30 strawberry cups in there out of 100. And when I reduce that, it becomes 3 out of 10, or if you use the decimal, it's 0.3. Remember, you don't need to do both of those, one or the other. You either wrote down 3 over 10 or 0.3. Both of those are correct, acceptable. I will mark it 100%. Just pick your favorite. The next one, the probability of vanilla or chocolate. Okay. I'm sorry, what'd you say? Yeah, there's 40 vanilla, there's 10 chocolate, so that is 50 of those events out of 100. So you have a 0.5 or a 1 out of 2 chance of picking a vanilla or chocolate. And then the last one is the probability that it's not mint, because mint ice cream is disgusting. What is the probability that it's not mint? Yeah, so there's 20 mint ones. So if you're going to be non-maintenance, everything else, so that's 80 out of 100. So that's 4/5 or 0.8. Any questions, comments, concerns about that problem right there? All right, well, the next problem I put on here was just an example of reading a table, because there are going to be many tables as we go through this chapter. So I just want to make sure to cover this. So I gave you a table of different vehicles and different breakdowns on a car lot. And so the first problem that we're going to do with this is at the bottom of the page. Is the probability that if I randomly chose a vehicle from this lot, what's the probability that it's a car? So I'm going to give you about 20, 25 seconds to determine what you think the probability of a car is. All right, according to this table, how many cars are on this lot? Yep, that is true. So right over here, there's 85 cars. Now I could ask you about specific cars. 55 of them are General Motors cars and 30 of them are Toyota, but I didn't ask for any specifics. It's 85. Out of how many total cars are on this lot? 200. Perfect. Sounds like you're this first one, you're reading the table okay. If you're not reading the table okay, just raise your hand. I'll walk around. On the top of the next page, there are 4 more problems for this table. So go ahead and do those, and we'll talk about those in a minute. So if you need help, raise your hand. Happy to come around and help out. All right, so the first one, again, we're just practicing reading this table. So the probability of an SUV, how many SUVs are there on this lot? Okay, 45 out of the 200. That is fantastic. And so when I pop that into the calculator, I get 0.225. Everybody comfortable with the numbers that I throw out there? Anybody get something different we got to talk about? Okay, what's the probability of a Toyota? How many Toyotas are on this parking lot? Okay, out of the 200, so we have 77 divided by the 200, and so that's 0.385. Okay. So now we're reading a little bit of a different thing on the table. The next problem, what's the probability it's a truck made by GM? How many of those are there? 40. Okay, there are 40 out of the 200 of those. That's fantastic. And I believe that's going to be 0.20, but let me, still a little early in the day for mental arithmetic. And then the last but not least, not a car. So you told me earlier there were 85 cars. That means there's how many not a cars? Perfect. Excellent work. Love it. And so then 115 divided by 200 is 0.575. I'm just going to keep working through examples. If you got a question, stop me, let me know. Decks of cards, a deck of cards is used a lot, especially in our book, just because there is enough outcomes to keep it interesting, but there's not so many outcomes that the numbers get really bulky. I don't assume anybody in here is familiar with a deck of cards. I don't know how much cards you play. When I was in college, we played a bit, but I don't always assume that. So I will always give you the picture of the deck of cards when I have a problem that you're going to do for me regarding that. So just some constraints, some things to know about the deck of cards. The reason that it's used a lot is just the symmetry. Our cards are labeled, the A is ace. In this class, if you are a card player, we will count the ace as the number 1, okay, just to keep things nice and simple. Ace is the number 1. So you've got 1 through 10, and then the jack, the queen, the king, these are called commonly either the picture cards or the face cards. No, there's 52 cards total. Okay, if you count them all up. So let me write that over here. Should have left myself a little more space. So I'm learning as we go too. So there's 52 cards total. They're divided into 2 colors. So there's half of them are black, half of them are red. Okay, so there's a lot of symmetry in your cards as well. So there's 26 black cards, there's 26 red cards. They're divided into 4 suits. I get these backwards a lot. I'm not great with shapes, but I think these ones are the clubs. These ones are the spades. These ones are the hearts. And then the last one are the diamonds. And so those are called the suits. Okay, I don't care if you know that word or not. I'm just letting you know what it is. So if there's 52 cards and I've got 4 different suits, that means that there are, and you can count them up, there's 13 of each of the different suits. Okay, and I think that's about all the detail that you need to know. So there's going to be 4 of each card. So there's 4 aces, there's 4 twos, there's 2 black twos, 2 red twos. So there's different combinations of things that can make for interesting problems, and that's why decks of cards are used for probability. So using that picture, exercise 5 asks you to do 6 problems on the deck of cards. If you could go ahead and make an attempt at those, that'd be fantastic. All right, so each of these problems is just a matter of counting. So if you get a different number than me, then let me know. First one's the probability of an 8. So I come up here. How many 8s are there in my deck of cards? Yep, there's 1, 2, 3, 4. I've given no other specifics. I didn't ask for a particular 8. So there are 4 out of my 52 cards. You can reduce that. That's going to be 1 out of 13. But 4 divided by 52 is going to be 0.0769. So pretty low probability that that's going to happen. The probability of a club. How many clubs do I have in my deck of cards? Okay, there are 13 out of the 52 cards. Fantastic. So that is 1 out of 4 or 0.25. We doing okay? All right, a picture card. When I come up here, when I count, how many picture cards are there in my deck of cards? Yep, they're right here. These 12 right here that are on the end are the picture cards. So there are 12 out of 52. And that'll reduce to 3 out of 13, or the decimal 0.2308. How many cards less than 5 are there? I'm sorry? There are less, it's less than 5. It's not less than or equal to 5. That's okay. It's great to make that distinction. So if I wanted, the answer would be 20 if I said the number is less than or equal to 5, because then we would include it. But since I just said less than, we're only going to consider these 16 right here, the ace through the 4 of each of the suits. Okay, so that is 16 cards out of the 52, which reduces to 4 out of 13. And that is 0.3077. How many red 7s are there in the deck? Yeah, there's the 7 of hearts and the 7 of diamonds. So that's 2 out of 52, or 1 out of every 26 cards. But that's 0.0769. And then finally, a heart that is black. How many of those are there? There's none. The hearts are red, so that's 0 out of 52, or that is something that cannot happen. As you're going through your probabilities, something to be aware of, statistics people consider something, if the probability is less than 0.005, that's called a rare event. Okay, so that's something that would be tough. Yes?
For a red 7,
yep.
I got 0.033.
0.03. Yes, so did I. I don't know how I did that. My apologies. I hit the wrong number. So for the red 7, that is going to be 0.0385. I appreciate you calling me on that. So hit the wrong button this morning. Any other questions? Anything else I goofed up here? All right, well, we're just about done. The last thing as you go through your homework that you're going to see on probability is probability equated with area. So like if you like to throw darts and you know you're going to hit the dartboard, you can figure out the probability that you're going to hit certain spots. And so exercise 6, I think, is the simpler of the examples because all of the spaces are cut up into equal parts or equal size parts. So give exercise 6 your best attempt. And if you don't quite get it, you're going to get to redeem yourself on exercise 7. Okay, so probably it's red. How many of the spaces on this spinner are red? 4. And notice we can do that because all of these spaces are diced up into equal size pie slices. So I've got 4 spaces out of the 8 that are red, so that is a half or 0.5. So also notice this. If I was just to clump these spaces together, the red spaces take up half the circle. Okay, so there's a relationship between the amount of area that something takes up and its probability, okay, which is what I'm trying to show with this example. How about the green? How many green spaces are there? Okay, 3 out of 8, and I'm not even going to pretend to try to do that while I'm talking. That's 0.375. Yellow? Yep, or 0.125. And then last but not least, how many not yellow spaces are there? Which is 0.875. Great. So 87.5% of this circle is not yellow. 12.5% is yellow. Sometimes you do see probabilities written as percents. So we could write this as 50%. So just know that if you come across an example in the book and they give you a percent, that's the same thing as your probability. So the last problem, exercise 7, when you encounter something that maybe the spots aren't equally divided up, the easiest thing to do on this problem is to take your pencil and say, okay, let me divide the spaces up in equal parts. So this green space, you can't just say the amount of green is 1 out of 3. Right? Because I know there's three pie slices here and the green is one of them, but they are all different sized. So the easiest thing to do is to take your pen and go, wee, and slice that one in half. Now you have equally sized parts, and you can go ahead and find your probabilities. So just going to give you a moment to finish that up, and then that is section 11.1. All right, so now that I've divided everything up into equal size pieces of pie, the probability that you get a red is 1 out of 4, or 0.25. Green is half of the circle, so you could have just said that straight away because it's pretty right in your face, but it's 2 out of the 4 spots, or half, 0.5. Yellow is the same thing as red, is 1 out of 4, 0.25. And then not yellow is 3 parts out of 4, or 75% of the circle is not yellow.